Thank you for the introduction. Before I start with the mathematical part, I would like to thank all of the organizers for making this event possible and also for giving me the opportunity to speak today in front of all of you. So thank you very much. Let's start talking about wave maps, in particular about existence and stability of corotational self-similar blow-up solutions to the wave maps equation, where the target manifold is not the perfectly round sphere, but a slightly perturbed version of it. And the idea behind that is that the existence and stability of these kind of solutions has already been proven. And our question was, does the same hold true if we slightly perturb the geometry of a target manifold? And the answer to this is yes, and this is what I'm going to talk about today. So let's start with a wave maps equation. We have a map capital U mapping from 1 plus d dimensional Minkowski space into a, for now, Riemannian manifold capital N, and they solve the wave maps equation in local coordinates if they satisfy the following semi-linear wave type equation. We will not consider this equation in full generality, but for special cases where the target manifold N is a surface of revolution, or more general, a warp product manifold. And as an example, let's start with a sphere. So we have a generating curve here, G. Here it's just the half circle, and then we rotate this generating curve 360 degrees in space to obtain a surface of revolution, here the D sphere. And on this D-sphere, then one can define coordinates on it. So first, latitude and longitude. And in these coordinates, every map U mapping from 1 plus d dimensional Minkowski space into the D-sphere can be written in those coordinates. And we furthermore will restrict our attention to so-called corotational wave maps. So they respect the symmetry of the Minkowski space and the D-sphere. So what it essentially does, you can first map into the sphere and then rotate, and this should equal the same as if you first rotate in Minkowski space and then map into the D-sphere. Mathematically, the first component should be independent of the angle omega, and the second component should be equal to the identity in the angle omega. And if one plugs this ansatz into the wave maps equation, one obtains a radial d-dimensional semi-linear wave equation for the radial profile small u. This equation you might have already been seen, but let me now, for now, quickly recap some known results about this equation. So first of all, we know that for every energy supercritical dimension d greater or equal than 3, there exist self-similar solutions to this equation. And more precisely, those self-similar solutions are even known explicitly in closed form. More precisely, we have for every blow-up time capital T, we have that the blow-up solution U0 capital T is can be written as a self-similar profile F0 in similarity coordinates, so R divided by capital T minus small t, and the self-similar profile F0 is essentially the Arcus tangents. And they solve the equation, and they also suffer a gradient blowup at the origin as t approaches the blowup time capital T. And not only do we know that self-similar solutions exist, but in particular, this family with capital T as a parameter is known to be asymptotically nonlinear stable against small perturbations. And actually also in various settings by now, so in particular, maybe in backwards light cones, in global similarity coordinates, which we will be adapting, and other various settings. So this is essentially what has been known for the sphere. And we will now, or we showed kind of the same results, so existence and stability for target manifolds, which are slightly perturbed versions of the sphere. So let me introduce you our concept of perturbed spheres, or how we think about perturbed spheres. Here's, first of all, a picture, probably poorly drawn, try of me to visualize a perturbed sphere. So maybe let's focus on the mathematical part on the right-hand side. So here we have a generating curve of a warping function, should be g epsilon. And in the, let's say, main order, leading order term, it is the exact precise warping function as we have for the D-sphere. And now we have a kind of epsilon small error term, and think about alpha as being a small bump function. So here, let's see for the picture, we have a half circle, but then we have a small perturbation or small bump function around it. And this generating curve, we rotate 360 degrees in space. So here one can as well define the concept of corotational wave maps. And again, if we plug this ansatz into the wave maps equation, we obtain again a semi-linear radial wave type equation for the radial profile. And everything actually stays the same except for the nonlinearity. Here we have, instead of sine of u times cosine of u, we now have the warping function g epsilon times the derivative of the warping function g epsilon. And I've written down it in the following form to heuristically make clear, okay, the only term which does not depend on epsilon is precisely the nonlinearity coming from the d-sphere. So heuristically, this is a really rough idea how it might work, what we are going to show. So maybe let me be a bit more precise. Our first result will be about existence of self-similar solutions to this equation, but this is actually not completely new. So the pure existence of self-similar solutions to these type of target manifolds has already been shown by Chatin and Tachwilder-Zadeh, and actually for even more general warp product manifolds. But the essential new gain from our perspective, or from our work, is that since we are somehow close to the sphere, we can also construct self-similar blow-up solutions, which are somehow close to the already known blow-up solutions coming from the d-sphere. So let me be more precise. We know that if we chose a parameter epsilon star sufficiently small, we know that all smaller parameters in every blow-up time capital T, there exists a self-similar solution, u epsilon capital T, which suffers a gradient blow-up. So this is essentially already known, but the new part is, okay, we actually have this following decomposition of a self-similar solution, especially the self-similar profile f epsilon. You can write it as f0, which is the self-similar profile coming from the d-sphere, plus an epsilon small perturbation phi epsilon. And this also depends Lipschitz continuous on the parameter epsilon. Maybe let me tell you a quick, really rough idea how one would go on to prove this result. So first of all, one divides everything by r to obtain then a d plus 2 dimensional semilinear radial wave equation. And the main gain here is that the nonlinearity is now generated by a smooth function. Then one introduces, reformulates this equation as a first order problem and introduces similarity coordinates to obtain an evolution equation. And for this evolution equation, we are now looking for static solutions. Self-similar solutions become static in similarity coordinates. And our ansatz is, that's also how we construct the blow-up solution, is just by making this ansatz, so psi epsilon should be equal to psi 0. This is the blow-up solution coming from the sphere plus an epsilon small perturbation phi epsilon. And we hope to solve for this phi epsilon. So one plugs this ansatz into the equation and then linearizes in phi epsilon. And the naive approach would now be to put the linear part on the left-hand side of the equation and then try to invert this linear part to obtain a fixed point equation for phi epsilon. The problem is that the potential L epsilon prime is depending on epsilon, and later on we need actually uniform estimates with respect to this parameter. And to overcome this problem, the main idea was actually to split the potential into two parts. One part which depends still on epsilon, but is kind of epsilon small, so we can leave this part then on the right-hand side and only put a part which is independent of epsilon on the left-hand side. And this part is actually precisely the linearized operator which comes from the case where the target manifold is the d-sphere. And there we can use the fact that the stability of this blow-up solution has already been shown. In particular, the spectrum in some function spaces is contained in a left-hand half plane, except one unstable eigenvalue lambda being equal to 1. But the main part, or the crucial part here for the existence proof, we only need that 0 is not in the spectrum. So, and this is the case here, so we can invert this operator to obtain a fixed point equation for phi epsilon. And then if we transform everything back in physical coordinates, we have shown the existence of a self-similar blow-up solution. So now that we have constructed such a blow-up solution, let me show you our main result, namely that we can also show the stability of these constructed blow-up solutions. So first of all, how to read this theorem. First, we have, again, for every energy supercritical dimension, d being greater or equal than 3, we set the real space dimensions, n being equal to d plus 2. And then maybe let's have first a look at the Cauchy problem, or the perturbed Cauchy problem. V epsilon of 1 is the original blow-up solution now for perturbed spheres, and the blow-up time is set equal to capital T equal to 1. And then we perturb these initial data slightly by phi 0 and phi 1 being radial Schwartz functions in some intersection homogeneous Sobolev spaces, so small inverse spaces, where the first exponent S is arbitrarily close to the scaling critical exponent, d half, or here n half minus 1. And the second component, k, is some arbitrarily large parameter, so that we at least have an L infinity or even C2 embedding. So then essentially what the theorem says is, if we restrict the parameter epsilon small enough, we know that there exists another blow-up time, which must not necessarily be equal to 1 again, but close to 1, capital T, which depends on epsilon, such that we obtain a unique classical solution, V epsilon, to the perturbed initial Cauchy problem. And this V epsilon can actually be decomposed at now the original blow-up solution, which blows up at time capital T, plus a perturbation phi epsilon, which is not necessarily static anymore. And this converges asymptotically as T approaches the blow-up time capital T back to the original blow-up solution at time capital T, at now time capital T. So I think I might be over now. So I think I'll skip the stability proof and just thank you for your attention.